This talk is about electromagnetic diffraction modeling and simulation. First, fundamentals of modeling and simulation, MODSIM, will be discussed. Then, the definition and examples of radar cross-section, RCS, will be given. Finally, diffraction will be outlined with the canonical 2D wedge problem. A few other examples will also be included before the conclusions. Here you see the definitions of keywords like model, simulation, and simulator. We always use models, but do the simulation very often when it is expensive, time-consuming, or dangerous to do tests with real systems. Sometimes we don't have the real system yet. Finally, if we have the simulator, we can play what-if type games. Different types of simulations may be of interest, but what we will focus on this talk is physics-based simulation. This means computer or numerical simulations based on physical understanding and mathematical representation of a real problem, device, or system. We engineers deal with real-life problems, and we do that using math and computers. This slide shows basic elements of MODSIM. How far do you need to go in modeling and simulation? This is a key question, and the answer depends on the accuracy you need, depends on the problem you deal with. Building a model means introducing approximations, assumptions, and simplifications. It also means to neglect several factors. If you use simulations, finally this means you do discretization. You have to take into account the effects of all these. This slide shows the definitions of validation, verification, and calibration from the guide of AIAA. Validation asks the question whether you built the right model. Verification asks the question whether you built the model right. Finally, calibration is nothing but testing the results against reference data. Terms, definitions, and processes of physics-based modeling and simulation are given in this slide. We validate our model first through analytical modeling. Then we write our code and verify it via computer programming. Finally, we do numerical or real experimentation to calibrate the data. All these steps necessitate well understanding and using of signal and data processing. The next few slides are about electromagnetic scattering. Electromagnetic waves interact with objects and scatter. Scattering includes reflection, refraction, and diffraction. Edges and tips of an object cause diffraction. Source-induced currents can be divided into two: uniform currents and non-uniform currents. Non-uniform surface currents excite fringe fields. An instant from a 2D FDDT simulation is given in this slide. The red circle on the left is the line source. Region 1 shows the forward propagating waves. In region 2, propagating and ground reflected waves are observed and their interference is given. In region 3, multi-reflections are observed. Finally, the diffraction contribution from the right tip of the first object is given in region 4. These two videos are about a PEC strip hit by a plane wave. On the left, total fields are given. On the right, only scattered fields are recorded. The same example, but a plane wave from a different angle of illumination. The same scenario, but the edge illumination. Only the scattered fields with two different plane wave illuminations. On the left, the plane wave hits the hard side of the strip. On the right, the plane wave hits the soft side of the strip. RCS, radar cross-section, is a parameter which defines electromagnetic scattering of an object. In the simple radar equation, sigma in square meter represents the RCS. RCS of a target depends on its size, geometry, and material, as well as the radar frequency. Low visible target can be designed by understanding electromagnetic wave target interaction. As you see from this slide, plane wave hitting a target may cause specular reflections, surface waves, creeping waves, diffraction from aircraft nose, returns from engine cavity, edge diffraction, multiple reflections, and so on. RCS prediction is one major task in electromagnetic engineering. It can be done through measurements, mathematical and analytical modeling, or numerical techniques. RCS measurements may be indoor, in a compact range, or may be outdoor, which are both expensive and time-consuming. At this point, I would like to present our RCS package, which we introduced back in 2008. It uses two different numerical methods, FDDT and method of moments. The paper and the package can be downloaded from the IEEE site or our web pages. Any object with 3ds graphics file can directly be given to this package. Then the package automatically discretizes this target and discrete FDDT and MOM models are created. The package then presents FDDT and MOM results of RCS. The target in the previous slide was DC10. Here you see F16. Here you see the picture of a target, its 3ds graphics files, and the two discrete models created by the package. One beauty of this package is that you can visualize, observe transient time domain behavior of electromagnetic wave target interaction. You can do this recording with the target as in the previous video, or without the target as in here. Scattered waves around a frigate captured at different time instants during the FDDT simulations. Here is another example. RCS versus angle for a given angle of incidence can be obtained and plotted with this package. In order to do that, you first supply the 3ds graphics file, then choose your discrete parameters and run the FDDT, run the Fourier transform, discrete Fourier transform or fast Fourier transform, and then plot RCS versus angle graphics. RCS versus frequency graphics can also be obtained with this package. Here you see two different air targets with two different angle of illuminations and their RCS versus frequency graphics. Another example with Boeing 747. As we said before, once you calibrated your package, you can easily play what-if type games. For example, what if two air targets fly side by side or one on top of the other? How does the total RCS change? For the given scenario in the picture, the red and blue curves belong to 1 and 2 F16 targets. As you can see, RCS of single target or double target may be high or low depending on the frequency and other parameters. One important component of scattering is diffraction. The rest of this presentation belongs to physical understanding, mathematical foundation, and numerical simulations of diffraction. It can be said that the study of diffraction went back to Grimaldi. Early analytical studies are usually called high-frequency asymptotic methods. There are two kinds of high-frequency asymptotic methods: the ray-based and induced source-based approaches. The first group includes the geometrical theory of diffraction, GTD, and its various extensions such as UTD, Uniform Theory of Diffractions. The second group includes physical optics and physical theory of diffraction. The GTD was first introduced by Keller. Then Huyumjian and Patak modified GTD and introduced UTD. The father of PTD is Pyotr Ufimtsev. He is a colleague of mine and we have collaborated with him for the last 10 years. We published our first paper in the Antennas and Propagation magazine of the IEEE in 2011. The first author was one of my postdocs. In 2D, wedge with non-penetrable boundaries is a canonical structure where you can easily teach, learn, and observe different wave pieces, such as incident field, reflected field, and diffracted field. Initially, there are two different scenarios depending on the location of the source. The blue represents single-site illumination, the red represents double-site illumination. In acoustics, the problem is postulated with these two equations. The first one is the wave equation, the second one gives the boundary conditions. If the field at the surfaces of the wedge is zero, it is soft boundary conditions. If the normal derivative of the field is zero at the surface of the wedge, then this corresponds to hard boundary conditions. In electromagnetics, soft boundary conditions means transverse magnetic, hard boundary condition means transverse electric case. Chapter 10 of my recent book, Electromagnetic Modeling and Simulation, published by the IEEE Press in 2014, belongs to these high-frequency asymptotic techniques. This problem has both analytical exact and high-frequency asymptotic solutions. In 2011, we have published a tutorial in the Antennas and Propagation magazine of the IEEE, where we summarized all these analytical methods and developed and shared a nice diffraction package. This video shows the structure of this package. The user can select the structure, wedge exterior angle, incident distance, and source types. Boundary conditions may be soft or hard. Both total and diffracted fields may be observed. The user also selects the types of the solution, which are the exact solution, PO solution, PTD solution, UTD, and parabolic equation solutions. Once the plot button is pushed, the program starts. The progress of the program is given at the bottom left. The output may be diffracted field versus angle, total field versus angle, or frequency variation of scattered fields and total fields. After the introduction of this package, we asked a question. Can we do the same with FDDT, method of moments, and finite element, and discriminate these wave pieces? The answer is yes. Wedge diffraction with FDDT is included in chapter 14 of my book, Electromagnetic Modeling and Simulation. This slide shows the classical FDDT approach. You put your object inside the FDDT domain, send the input pulse, and observe time domain response. Then you do FFT and get the frequency behaviors. Here you observe a pulsed cylindrical wave hitting the wedge and scatter. Here, signal versus time during the FDDT simulation at one receiver is given. If incident, reflected, and diffracted pulses are separated in time, time gating can be applied and diffraction coefficient can be obtained with this FDDT method. Unfortunately, this happens rarely. In order to get and distinguish incident, reflected, and diffracted fields under any circumstances, we introduced a multi-step FDDT approach. This is the front panel of the FDDT diffraction package prepared by our group back in 2012. The user selects the parameters, run the package, observe the time evolution of scattered fields, and then get the total and diffracted fields in the frequency domain. The multi-step procedure is almost the same with the method of moments. Wedge diffraction with the method of moments is given in my book, Electromagnetic Modeling and Simulation, in chapter 13. Here you see total fields and diffracted fields around the wedge. The interior angle of the wedge is 60 degrees. The boundary condition is soft. Almost perfect agreement among the methods UTD, MOM, FTDT with the exact series are observed. VV&C divides source-induced currents into uniform and non-uniform parts. Uniform currents appear on planar pack surfaces. Non-uniform currents are caused by edge and tip type discontinuities. If we can separate them, then we can obtain fringe currents and fringe waves. We obtain fringe currents and fringe waves with the help of this two-step scenario. First, we use wedge scenario, then we use infinite plane scenario. Subtracting the results of the second from the first yields only non-uniform currents. Here you see total currents, uniform currents and non-uniform currents on both sides of the wedge. Fringe fields around a 90-degree wedge obtained via finite element method. Fringe waves versus angle of incidence. Here you see fringe waves around the wedge under soft and hard boundary conditions. The blue curve is PTD and the red curve is MOM. They agree very well. MTPO, the modified theory of physical optics results, is given by black curve, which fails to account for the fringe waves. If you are interested in the diffraction theory and wonder the deficits of modified theory of physical optics, then please get our IEEE Antennas and Propagation paper published in December 2013. We have published several papers where we obtained fringe waves around a wedge with PTD, method of moments, finite element method, and FTDT. We also published a paper where we share all the codes of the source codes of these methods. Double tip diffraction modeling using FTDT and method of moments is our next example. Here you see total fields, diffracted fields and scattered fields around the object. The thickness of the pack object is λ/10. The observation circle has 8 lambda radius. The boundary conditions are soft. Both FTDT and method of moment results are presented. The same with different objects. Here, the thickness of the object is lambda and the boundary conditions are hard. Here, the object is a horizontal strip with 5 wavelength width. The boundary condition is soft. We also used finite element method in double-tip diffraction modeling. Here you see method of moment, UTD, and finite element method results altogether. The last example belongs to triple diffraction. We obtained these results by finite element method. And the conclusions. The progress in numerical modeling and simulation is very impressive. Therefore, researchers and scientists and engineers have to pay attention to MODSIM and VV&C. We need to well understand the physics behind the mathematics and computer models. If possible, we need to compare the simulation results with reference data, in many cases, experimental data. We have to keep in mind the assumptions and validity ranges and check the accuracy. We need to look at the object as a whole, but also we need to pay attention to every details in terms of different electromagnetic phenomena and their contributions. High-frequency asymptotics have long been used in diffraction modeling. The geometric optics can model reflections and reflections, but fails to account for the field intensity in shadow regions. The GTD describes diffraction everywhere except at and near the incidence and reflection shadow transitions. The UTD removes this discontinuity along these shadow boundaries. However, GO, GTD, and UTD fails near caustics. The PTD supplements PO to provide corrections that are due to diffractions at edges of conducting surfaces. VV&C suggested the existence of fringe currents in addition to the uniform PO surface currents. Here are the advantages of ray-based GO and GTD. It is simple, can be used to solve complicated problems, provides physical insight, and may yield quite accurate results. In addition to all these, it can be combined with other techniques, such as the method of moments, to form a hybrid method. And these are the advantages of PO-PTD. They provide only the first asymptotic terms. They are the maximum of what modern asymptotic theories can do for complex objects, and they are main need in engineering. They allow constructing relatively simple solutions of practical problems. They provide uniform asymptotics for the scattered field, which are valid both in the ray regions and in the vicinity of foci and caustics. They clarify the physical structure of the scattered field. They establish the diffraction limit of reduction of scattering by absorbing coatings. And finally, they can be utilized to develop efficient hybrid techniques. Today's well-known numerical techniques like FDDT, MOM, and FEM can be used in diffraction modeling and simulation of arbitrary objects. But please pay attention to the physical meaning of the diffraction coefficient, which is nothing but a high-frequency asymptotic definition notion. In 2D, their application is not a problem, but in 3D, depending on how much details you want to model, may create computer memory and speed problems. The intelligent way is again to hybridize high-frequency asymptotics with numerical techniques. This concludes my presentation. I hope you enjoyed it and found useful. See you in another seminar.